Okay, so our examples so far and our steps were about solving line integrals over curves in space of functions f of x, y, z, scalar valued functions. Now we're going to think about combining this idea of line integrals with vector fields like we've been learning about recently. So some vector field capital F of x, y, z, a bunch of arrows in 3D. And so now we've got our little curve C that we want to evaluate. And this is going to be how we denote this type of line integral. And what we're saying is your vector field is a bunch of arrows in 3D. I don't know, I'm just drawing it like that. Doesn't really matter what it is, but it has magnitude and direction everywhere. And what we're going to be trying to find is your vector field F when it runs in the same direction as you're traveling on your curve C. So we're still integrating over a curve. Now we're thinking about, actually, let me go ahead and write this as a function of 3 variables like I did before. So you have a vector field that takes on values everywhere in x, y, z. And now instead of just integrating over the length of C, you're integrating over the length and direction of C. F and C have to be heading the same way for you to add F to this integral. And so in words, what this line integral is doing is it's adding parts of F that run alongside the curve C. Again, this idea of integrals being a bunch of really small additions should be familiar to you. So we're just going to have lots of little tiny components of F that happen to go with C, add them all up as we go. And the easiest way to evaluate this type of line integral is with the fundamental theorem of calculus. And so this is going to work if F is conservative, then F is equal to grad F for some potential function F. And the integral over a curve of F dot dr is just going to be F, the function, evaluated at the endpoints. From Q to elemental PQ. That's fine. You can figure this out. Okay. So there's Q, there's P, your curve C runs between the two, and you look at the difference between your function evaluations. And I just want you to note, this is just like how you integrate normally. A to B of little g dx is equal to Actually, we'll do capital G inside. So you take the antiderivative of whatever's inside and you get the difference between them to evaluate an integral. This is exactly the same thing. When we learned about potential functions, we said finding the gradient that your vector field is. So finding the potential function whose gradient generates your vector field is like an antiderivative. So if you have to find the integral of a derivative where we've established the gradients are basically derivatives, of course you're going to look at the difference between the things that aren't derivatives, the antiderivative. So I just want you to know that that's the easiest way you can evaluate a line integral, and you should always do it if you possibly can. But you can't always, so we will go over the steps to solve line integrals, but this time for vector fields. And I'm sure just like last time, we'll have to pause here and then pick up the next video. Yeah, we'll go ahead and do the steps in the next video just to be safe.